Module 3, the title, Higher Order Linear ODEs and More Laplace Transform. Yeah. Part A, first, a few topics. We look at the basics of higher order linear ODEs. Then, we study Laplace transform on Heaviside function. Yeah. Okay. Yeah, let me change the pen color. All right. Yeah. 8.1, basic types of higher order ODEs. Yeah. Yeah. Let us write the standard form of higher nth order, this time nth order ODEs. General nth order ODE. Yeah. We use this capital F function. You know, this is the most general form. Okay? Yeah. So this F function is a multivariable function. Yeah, multivariable. Yeah. Then, for each variable, the first one we use x as the variable. Then the remaining variables, y prime. Yeah. So we know we use these functions. We treat them as different variables in this equation. Yeah. So and this capital F function can be very general. Yeah, general. All right, approach. Yeah, how to study. Yeah, we extend the result for the second order ODE. Yeah, second we have we have the way we have developed. Yeah. Can we generalize to higher order? Right? For example, the Wronskian, that determinant we can generalize easily. Yeah. So then, other formulas, can we do the, using the similar way to generate the result? Yeah. All right. So yeah, we will study. Yeah. Then, there are these 4 types of higher order ODEs. We can study it. The first one, the standard form of linear ODEs. Yeah. Because that capital F is too general. Yeah. So we want to study some easier. Yeah. Yeah. Linear, yeah, especially linear, yeah, because this general, it's very hard to control that linearity property. Yeah. So in order to get a linearity property, yeah, linear, so we use the specific form like this. Yeah. All right. So, yeah. So it's the standard form is a non-homogeneous linear ODE. Yeah. The second type, yeah. Yeah, because the first type is just a portion of the generals. Let me use this big circle represent this general ODE. Then the first type, just a smaller circle inside that general type. Yeah. And we have many other forms. So those ODEs that can be represented by the general form of ODEs, but cannot be represented by the standard form of linear ODE. Yeah, so you can see the remaining part. Yeah, okay, yeah, inside that big circle. That's the second type. Then, third type, homogeneous linear ODE. Yeah, so that R function 0. Yeah. The fourth type, initial value problems. But this time, initial value, we need to, so here you see the initial condition. Yeah. Y, x0, y prime, that. For all so you need to provide the initial values for the original function at one point and all their derivatives value. The values for all orders of the derivatives at the same point. Here, at the same point. Yeah. All right. Yeah. Yeah. All right. Yeah. So then that's the, the basic types. Yeah, we can study. Yeah. Yeah. But this second type is the hardest. Okay. The second type is the hardest. Yeah. Yeah. So we can only work on some very special second type. Yeah. The general. So we couldn't solve the general second type equations we cannot solve. Yeah. But some very, very special type second, yeah, then we can solve. Yeah. All right. 8.2, basis of solutions and linear independence. Now we need to generalize that Wronskian concept for the basis of solutions, nth order ODEs, the solutions. Yeah. Similar, yeah, this result similar to the one we have for the second order, existence uniqueness theorem. Yeah. So straightforward generalization. Yeah. Yeah. Homogeneous, yeah, ODE. Yeah. How do you know this equation, there exists a solution for this equation? Yeah. So the first result, yeah, all right, for this IVP problem, yeah, the condition, the coefficient functions are continuous on some open interval I open interval. Yeah, continuous. We only require. So that's the same condition we use for second order homogeneous linear ODE. Yeah. Yeah. So then the initial value problem has unique solution. Okay. Has unique. So here this result covers both existence and unique. Has, that's the existence, right? Then unique, yeah, solution y of x on I. Yeah, that's the first result for the generalization of the second order result. Yeah. Then superposition principle. Yeah, that's easy to see. The superposition, yeah, linear combination, right? Yeah, linearity principle also. Sums and constant multiples of solutions, yeah, for the above homogeneous ODE, again solutions on I. Yeah. Yeah. But this principle does not hold for non-homogeneous or non-linear ODE. Yeah. So you should be careful when you apply, yeah, this principle. Yeah. All right. Then let's study linear independence and dependence. Yeah. Similar to the way we studied for the second order ODE. Yeah. Yeah. The result is quite similar. Yeah. So let's look at the result. Yeah. We call y1 ... yn linearly independent definition of. How do you define these n functions? Yeah. So here you can see. Although later we will use these y1 through yn as the solutions for the homogeneous nth order linear ODE. Yeah. But here, when we define linear independence, we do not require solutions, right? Yeah. Linear independence, when we make this definition, that's for the general functions. Yeah. Just to get n different functions. Just give us n different functions. We can check if they are linearly independent. Yeah. Nothing to do with any ODE. Yeah. N arbitrary functions. Yeah. y1 through yn. we can define if they are linearly independent or not. Yeah. All right. The definition is like this. Yeah. If we can find constant k1, k2 through kn constant such that the linear combination of these n functions equal to 0 on the whole open interval I. So here we know that it's an open interval I, okay? Yeah. On the whole interval I. Yeah, it's true on the whole interval I, not just on one point, okay? On all the points on this open interval I. Yeah. 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 Implies that, yeah. So if it implies that all the k coefficients, all these n k coefficients must be 0. Okay? So if you make this 0, then it forces all the k coefficients 0. If you have that, then we say these n functions are linearly independent. That's definition. Yeah, here. Is it? Yeah? Yeah. All right. That linearly dependent. Yeah. Linearly dependent we call y1, these n functions, nothing to do with solutions of any ODE, linearly dependent on this open interval I if the equation k1, linear combination of these n functions, equal to 0 on I holds for some non-zero. Yeah, so not all 0. Some part of them 0, it's okay, but not all 0. So these k constant, k1, k2, k3, kn, not all 0. Not all. Then we say these n functions are linearly dependent. Okay, yeah. The definition. That's, yeah. All right. Then, based on this definition, so the Wronskian, that result, we can derive from these two definitions. So here, but we do not calculate. It's very easy. Here, we just give the result. The definition of the Wronskian determinant, but this time it's a n by n matrix, the determinant of n by n matrix. N rows, n columns. Derivative. So each row corresponds to certain order of derivatives of these n functions. All right. So the Wronskian. Then we can use the Wronskian to tell us if these n functions are linearly dependent or independent. So there are two results. Okay. The first one, linearly dependent on I if and only if this determinant identical to 0 on the whole interval I. Okay? So this place, we use the identical to 0 condition. Then, let's look at the independent case. Independent case, linear independent on I if and only if that the Wronskian W not equal to 0 for some, only for one point. You only need 1 point, non-zero. Okay? The Wronskian not equal to 0, you only need, that is true for one of the points in that open interval I. Here you can see, for linear dependent, you require on all the points. The opposite case, because linear independent, that's the opposite case, right? Opposite case, that means the linearly dependent condition is not true. You negate that, right? You negate that statement. Yeah. When you negate identical is true, you only need to find one point that is not true. That's enough, right? That's enough to negate the whole statement. Yeah. So that's why, yeah, you only need one point on I. Okay? Yeah. So here I want you to, when you determine n functions are linearly dependent or independent, you should be very careful. Do you need to consider all the points on I, or you only need to find one point on I satisfying certain condition? Yeah, yeah. So because you may have those questions in your quiz or homework assignments. Okay, yeah, quiz or homework assignments. Yeah, yeah, yeah. Yeah. For your second homework assignment, I plan to combine quiz and homework assignments. So you only need to do one set of concept questions. Yeah, yeah. Let's say quiz number 3. Quiz number 3 is also treated as the part A of homework assignment number 2. Yeah. In this way, I can give you fewer questions in homework assignment number 2. Yeah. Because we need to prepare for the midterm. So we do not have that much time. So we need to, combine the 2 assignments. Yeah. Yeah. All right. Then, third order Euler-Cauchy equations. Yeah. That's pretty straightforward. Yeah. So this generalization, very straightforward. Yeah. So, yeah. Let me quickly go through. Yeah. So, look at this example. Yeah. Initial conditions. Yeah. Then, yeah, we just apply the similar method we used for second order. Yeah. Characteristic equation. Yeah. But this we use. This special assumption. Yeah. Y with the structure, a power function of x, but m not necessarily integer. Yeah. So m, any real number. Yeah. Even complex number, right? Yeah. Because complex number we will use sine cosine. Yeah. So even complex number is allowed for m value here. Yeah. All right. So y prime, y double prime. Yeah, so now then triple prime. Yeah. All right, this time, yeah. Then we plug in, yeah. After simplification, we get this cubic polynomial for n variable. Cubic polynomial. So you need to solve a cubic equation. Yeah, cubic equation. Yeah, much harder to solve. Yeah. But for this class, yeah, because you may have chance to need to solve higher order equations, higher order polynomial equations. Yeah, I allow you to use Wolfram alpha to solve. So you can use Wolfram alpha to find the solution. Yeah, yeah, it's okay. Yeah, yeah, it's legal. Yeah. All right. So you do the factorization. Yeah, here if you do that's the factorization. That's the final factorization. Yeah, because the Wolfram alpha can give you factorization immediately. Okay. Yeah, for the equations as simple as this one, so you can get the factorization easily. Yeah. All right. Then you have 3 solutions. Yeah. 3, because these 3 roots of the equation, they are single roots. Yeah, we know single roots. Yeah. So the 3 solutions, y1, y2, y3, yeah, just use the single roots directly. Yeah. Yeah. m1, m2, m3. Yeah. So you have 3 solutions. Yeah. All right. Then we need to find appropriate C1, C2, C3 constant. Yeah. 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 Then you just, plug in these three initial values, you get 3 equations. So then you need to solve a linear system. Okay? Yeah, solve a linear system. Yeah. Yeah. And you're also allowed to use Wolfram alpha to find solution. Yeah. So, yeah. So that is solution. Okay? Yeah. But if you know how to use, yeah, I think it's very powerful. Yeah. For questions as simple as these questions, it's very easy to find a solution. Yeah.
When you say solve, do you mean like do the RRAF matrix, like just for the constants, or what do you
solve
for like the intermediate steps, like boiling, like the RRAF matrix?
Decomposition? Yeah. Yeah. You do not need to show me the technique, okay? Yeah. You do not need to show me the technique, yeah. So you may talk about, special technique, yeah. We only need to get the final solution, yeah. Yeah. Intermediate step you can skip, okay? Yeah, from this step to this step, all the intermediate step you can skip, okay? Yeah, on your scratch paper, yeah. Yeah, yeah. Yeah, for us, we know if you can find the correct solution, yeah, that's good. Yeah. But we want to, yeah. So our main focus is on the before, yeah, because this already near the end, yeah. So then I do not need to see your detailed work, yeah. Yeah. Before that, the work before that, yeah. How do you get this step? Yeah. Now I need to see the detail, yeah. Yeah. All right, yeah. So that's a simple example, yeah. So the final solution you can find, yeah. So at the end, actually we do not need to do it, but here just we want to check our, Wronskian, how to use Wronskian to see the linear independence. Yeah. So here let's calculate the Wronskian on these 3 equations. Yeah, on these 3 equations. Okay. Yeah. Yeah. So I hope you know how to calculate the determinant. Yeah. So but for the determinant, you can also use the calculator. Okay. Use that Wolfram alpha, that kind of calculator you can find. Yeah. So I do not need your intermediate steps. Okay. Yeah. 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 So it's okay. So you if your calculation is correct, yeah. So the intermediate steps, yeah. So that's the yeah, not important, yeah. For us, yeah. All right. Yeah. So this is the standard form. Yeah. Same equation, but we write it as a standard form. Yeah. Yeah. All right. Yeah. The general solution. Now we go to the general solution. Yeah. First, look at the homogeneous case, the general solution. Yeah. That here we generalize the results from second order. Second order, we have similar results, but the extension from the second order ODE, yeah, pretty straightforward. Yeah. Homogeneous equation, so that's the, equation number 2 here. Yeah. We only need the coefficient functions. Yeah, these coefficient functions continuous. Yeah, so it has a general solution. Yeah, actually, this one we had it before, right? Yeah, in a previous slide, we have this. Yeah, but the second part, we didn't have in the previous slide, but the second part we have it for our second order ODE. So this is just straightforward generalization. The second part is general solution includes all solutions. That's the, statement. Yeah. The meaning is if, yeah, equation 2, yeah, this equation 2 continuous, yeah, only continuous coefficients, yeah, on some open interval I, then every solution y of 2 can be represented as a linear combination of n functions, and these n functions form a basis of the solution. Yeah. So that's the result. Any, because this here is every solution, right? Every solution. Okay. Yeah. Every solution can be represented as a linear combination of these n basis functions. That's a generalization from our second order result. Yeah. In other words, yeah. So what's the significance of this one? Yeah. Because you feel it's quite natural, right? What's the significance? The significance here is no singular solution for this type of ODEs. Because there is a singular solution concept, right? Yeah, singular. So what's the singular solution? Singular solution, that solution cannot be represented as, so it is a solution, but that solution cannot be represented as that form. That's the singular solution. But this theorem tells us there is no singular solution for nth order linear homogeneous ODE. Yeah. But with this kind of continuous, yeah, that condition, yeah, minimum condition, yeah, that condition. Okay, yeah. All right, so that's all generalization. So far, all these results are the generalizations from the second order, those of second order ODE. Yeah. All right, next, 8.3, homogeneous high order ODE. Yeah. So these results also the straightforward generalization. So you can see these results also the generalization of second order ODE. Okay, yeah, yeah, the standard form, yeah, yeah. But here, yeah, when we look at this form, all these coefficients are the constant coefficients. Yeah, because the title constant coefficients. Yeah. All right, then we use the same way. Yeah. So here, solve characteristic equation. Yeah. So we take a y equals e to the lambda x, so we can get a characteristic equation, the algebraic equation. Yeah. But here, y parenthesis, right? Look at that. Y parenthesis. Because parenthesis usually we use to represent derivative, right? Yeah, so here, yeah, because this one I copy from the textbook. Yeah. I take the screenshot. Yeah. So because here lambda is a number. Yeah, could be complex number. Lambda. So here lambda is a complex number. Yeah. Then for a number, we do not take derivatives, right? The derivative is 0. Yeah, it's not a function. It's a number. So it's not derivatives. They are the exponent. Yeah. All right. But in order to find the roots, yeah, because this is algebraic nth order. So this is an nth order algebraic equation. Okay? So here we need to solve an nth order algebraic equation. Then there is a famous theorem I mentioned before. Yeah, remember? Yeah, when I explain, the basis when we compare coefficients, I talk about this fundamental theorem of algebra. Yeah. Now let me give you the statement of that theorem. Every non-zero single variable degree n polynomial with complex coefficients. Okay? complex, so this time, this coefficients complex. So these little a coefficients, they are allowed to be complex numbers, not necessarily real numbers. Yeah. You can see this theorem is very general. Even for complex numbers, coefficients, yeah, has counted by multiplicity. Multiplicity of a root, yeah, I remember I explained before, the multiplicity. Yeah. If you have, for example, you have a root y lambda minus lambda 0 to nth. Yeah. If you have this factor, although you have other factors, okay, other factors, but one of the root is repeated m times, we'll call this m as the multiplicity of this lambda 0 root, okay, yeah, counted with multiplicity, yeah, exactly n complex roots. Yeah. When you count the roots, so this y0, this lambda 0, you need to count m times, okay, because multiplicity is m. So lambda 0 counted m times. That's the multiplicity. Then you add all the counting numbers of all the roots. That number exactly n complex roots. That's the fundamental theorem of algebra. Fundamental theorem of algebra, right? All right. That means for this nth order, actually degree n. So we do not say, nth order different. Degree n. Yeah. So yeah, here I wrote nth order. Yeah, because degree and order, there is one difference. Yeah. I should write degree n. I should be very careful. Degree n algebraic equation. Yeah. Yeah. Because if the second order, for the ODE we use second order, right? We do not use degree, so we use order. Yeah. And here we use degree, but if you use order, then the meaning is different. Okay, the meaning is different from degree. Yeah. Yeah. All right. Yeah. So we should be careful. Okay. Yeah. Because the degree, if you use order, this will be n plus 1 order. It won't be nth order. For algebraic, okay, not ODE, okay, n plus 1. If you talk about the order, okay, yeah, degree, then we say degree n, okay, yeah, they're different. All right. All right. So now we use the fundamental theorem of algebra to give us the structure of all the roots. Yeah. There are n roots. Yeah. Then we can write the forms, explicit forms of all the n solutions of this type of ODE, homogeneous linear ODE with constant coefficients. Yeah. All right. Case 1, the first type. Yeah. First type, distinct real roots. Yeah. So that equation, so this characteristic equation has n distinct real roots. The simplest case, single roots, okay, distinct. Then you do not have the multiplicity higher than 1. Okay, yeah, n roots, yeah, different. All these lambda numbers are different. Then the solution is straightforward. So y1 e to the lambda 1 x dot 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 yn equals e to the lambda n times x. The first case. Second case, now we need to consider multiple roots. One particular root is repeated multiple times. Yeah. Let's say lambda is a real root of order m. Yeah. Order m, that means the multiplicity m. Okay, so here the order m also means multiplicity m. Yeah. Yeah. Because this order term is used everywhere. Yeah. Everywhere. Yeah. Yeah. And the meaning could be quite different. In different places, the meaning of this order could be quite different. Yeah. All right. Then, for related to this particular lambda, we can write m roots like this. Yeah. Multiplicity m, so we should, we should find m different solutions for this equation. Yeah. So these are the m different solutions. Yeah. That's the type 2. Type 3, simple complex roots. Yeah. Complex, this time complex. Yeah. Simple complex. Yeah. Conjugate pair. Yeah. So here, yeah, you may have conjugate pairs. Conjugate pair. All right. Yeah. So I will talk about this conjugate issue after I complete these 4 types of solution. Let me explain this. Some property related to this conjugate pairs. Here. Yeah. Why, when we talk about complex roots, usually we need to look at the conjugate pairs. Yeah. Yeah. So there is some reason. Okay. There is some reason. Yeah. Let me delay that explanation, the reason explanation. Yeah. All right. So first, let me give you the result. Yeah. You have the conjugate pairs. Yeah. All right. Yeah. So that means conjugate pair. That means one lambda corresponds to the first complex number. Second lambda corresponds to the second number, but they are related. Yeah, because these 2 lambdas, they are conjugates each other in this way. Yeah. All right. Then we can use the real functions to write our solutions. We do not need to use the complex functions. So we can get around that complex number, complex number. Yeah, because people want to avoid using the complex numbers in their final solutions. Yeah. So here we have the 2 real solutions, yeah, corresponding to these 2 conjugate complex roots. Yeah. But that's the simple. Simple, that means simple here also means single. Okay. Single means the multiplicity m equals 1. Yeah. Also, called a simple. All right. Yeah. Simple single. Yeah. 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 Same meaning. Yeah. All right. Then type number 4. This time we consider complex roots with certain multiplicity. Okay. Multiple. Yeah. This time multiple complex roots. Yeah. All right. Multiple complex roots. Yeah. Then, first we have the 2 solutions from similar to that simple case. But after that, then we need to multiply x. Yeah. If you have multiplicity 3, you need to multiply x squared. Multiplicity 4, you need to multiply x cubed 1 by 1. Okay, 1 by 1. Yeah. Because here, your first time you multiply x, second time you multiply x squared, and so on. Okay, multiplicity m, the last one you need to multiply x to the m minus 1. Here, the same pattern, Yeah, but here because the space limitation, so here we only show the double case. Yeah. But you can easily generalize to the, m case. Yeah. multiplicity M case. So using the pattern from second type. All right. Then, so we have last a few minutes. Let me explain this conjugate pair a little more. Yeah. 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 So here I want to explain slowly, carefully, because for some students, you may get confused easily. Yeah. You may get confused easily. Yeah. All right. Let us, because the question is, under what situation we need to consider the conjugate pairs, right? Under what situations we consider conjugate pairs? Here, let me give you the conclusion. Yeah. All right. Yeah, I don't have much space here. Yeah, I just write somewhere. All right. So here, when these coefficients, okay, A0, A1, dot, 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 all these coefficients are real numbers, okay, yeah, numbers, yeah. Then you have the conclusion, okay? So what's the conclusion? Yeah. The conclusion is the complex roots appear in the conjugate pairs. Conjugate pairs, all right? Yeah? Okay? Yeah? So that means first you look at the coefficients if they are real numbers. Yeah. Most of the time they are real numbers, right? Yeah? In our real world application, most of the times they are real numbers. Then all the complex roots must appear in conjugate pairs. Okay? Yeah. Yeah. But why I want to talk about they are real numbers, not real? Because for the fundamental theorem of algebra, they are not required to be real numbers, right? Yeah. So because people, when they apply the fundamental theorem of algebra, then these A coefficients, they are not necessary to be real numbers. Yeah. They are allowed to be complex numbers. If they are allowed to be complex numbers, then you cannot expect the complex roots appear in conjugate pairs, okay? So that conclusion, that property does not hold. Yeah, does not hold. You cannot assume when you have for example, when you have the first complex root, you also have the second. You cannot assume that, okay? Yeah, if there is one of the coefficient that is not a real number, then you cannot use this conjugate structure to describe your complex roots. Yeah. Yeah. It must be all the coefficient must be the real numbers. Then you can use this property. Okay? Yeah. So you should be careful. Okay? All right. So let me stop right here. We finish this topic. Yeah. The next time we will do the Laplace transform. Okay? Yeah.